The modern internet is built on a mathematical limit. The IPv4 addressing system provides exactly 4.3 billion unique IP addresses. As the number of connected devices worldwide exploded, network engineers realized we were rapidly exhausting the entire global supply. Transitioning the entire global infrastructure to a new standard, IPv6, would take decades. To keep the internet functioning in the meantime, the engineering community created a stopgap measure, designated blocks of private, completely non-routable IP addresses. This standard is formally known as RFC 1918. It reserves 3 specific blocks: the 10 network for Class A, 172.16 for Class B, and 192.168 for Class C. Network administrators can assign these private IPs to devices inside their local networks with infinite reuse. Because these addresses are restricted to internal networks, they never conflict with external traffic, meaning they do not have to be globally unique. While that solves the local addressing problem, it creates a strict barrier at the network edge. Any device assigned an RFC 1918 private address is mathematically cut off from directly accessing the global internet. Look at this standard topology. We have a clear separation between the trusted green inside network, where our local PCs sit, and the untrusted yellow outside zone, representing the broader internet. If a packet originates from one of those internal PCs carrying a private source IP and attempts to cross into the public internet, external routers will immediately drop it. The global routing table simply does not recognize private IP addresses. To bridge this gap, an intermediary gateway is required. Here, Router 1 sits exactly on the boundary line, intercepting all outbound traffic before it hits the external network. The router executes a specific process called Network Address Translation, or NAT. As the packet passes through, NAT modifies the Layer 3 IP headers, replacing the private source address with a valid public one. By actively rewriting headers in transit, NAT acts as the essential passport control for data. Without it, modern enterprise and home networks would remain completely isolated from the web. The simplest implementation of this process is static NAT. This involves an administrator manually configuring a hard-coded one-to-one mapping between a specific private IP and a specific public IP. Here is what that looks like at the packet level. As the data crosses the router's egress interface, the source header is stripped. The original address of 192.168.0.167 is overwritten with 203.0.113.1. Cisco defines these specific stages with exact terminology. The original private IP address configured on the internal host, the 192.168.0.167, is the inside local address. Once the router translates it into a public, globally routable address, 203.0.113.1, it becomes the inside global address. When the external server replies, the router intercepts the returning packet. It checks its internal state table, identifies the active session, and executes the exact reverse translation on the destination header, routing it safely back to the inside local host. While static NAT successfully establishes internet communication, it requires one dedicated public IP for every single internal machine. It provides connectivity, but does nothing to preserve the shrinking public IP space. To reduce the administrative burden of manually mapping every single device, engineers use dynamic NAT. Look at this router configuration. Instead of individual lines, the administrator defines a NAT pool. This pool contains a continuous block of available public inside global addresses ready for use. Next, an access control list, or ACL, acts as a logic gate. It evaluates arriving packets to determine if their source IP falls within the permitted 192.168 internal subnet. When a packet arrives, the router checks the ACL. If the traffic is permitted, the router dynamically leases an available inside global IP from the pool and assigns it to that specific internal host for the duration of its session. Dynamic NAT removes the tedious data entry of static mapping. However, mathematically, it is bound by the exact same limitation. The translations are still handled on a strict 1-to-1 ratio. Because these addresses are leased out 1-to-1, a NAT pool can only support an exact number of active connections. If you have 10 public IPs in the pool, you can only support 10 concurrent outbound sessions. This chart displays what happens under load. As multiple internal hosts attempt to reach the internet at the same time, the available public addresses in the 100 network pool are quickly consumed. Once the 10th address is mapped, the pool is entirely depleted. When the very next internal host, 192.168.0.98, attempts to send an outbound packet, it hits a hard failure state. This condition is known as NAT pool exhaustion. With no available addresses, the router is forced to drop the packet entirely. Manipulating Layer 3 IP addresses alone fails to solve the broader IPv4 namespace shortage. To scale a network effectively, we have to break that one-to-one mapping limitation. We do this using port address translation, universally referred to as NAT overload. Instead of stopping at the Layer 3 IP addresses, NAT overload looks deeper into the packet structure. It targets the Layer 4 transport headers, specifically the port numbers. Instead of leasing different IP addresses, the router forces both internal hosts to translate their traffic into the exact same inside global IP, 100.0.0.1. To prevent data from colliding, the router appends a unique source port. One session gets port 54321, the other 54322. By factoring in Layer 4 port numbers, the router's simple, flat list of one-to-one translations is upgraded into a complex, multidimensional ledger capable of multiplexing outbound traffic. The math behind this multiplexing process is what allows the modern internet to function. Because these port identifiers are 16-bit values, the pool of available options is vast. A 16-bit address space yields over 65,000 available ports. This theoretically allows tens of thousands of active concurrent network connections to funnel through just a single public IP address. When external traffic replies, the router no longer looks at the IP address alone. It reads the unique destination port, references its translation ledger, and delivers the packet perfectly back to the specific private inside local address that requested it. This mechanism, NAT overload, serves as the ubiquitous protocol powering nearly all enterprise network edges and home routers worldwide. Through the synchronized manipulation of both Layer 3 network addresses and Layer 4 transport ports, PAT achieved what local subnetting could not. It prevented the exhaustion and collapse of the IPv4 internet, buying the global infrastructure the decades of time required to integrate IPv6.